Using parameters to control the appearance of some sort of visual output is an extremely common editing paradigm. When editing photos, you use a set of standardized parameters, such as exposure and contrast, shown here in Lightroom on the right, to change the appearance of the photo. When making a particle system in Unity, you use a much more complex but still finite set of parameters to define the look of a particle system. And many modern content creation tools allow experts to define their own custom parameter spaces to show to users. The parameters used for this cloth material are not the same ones that would be used for a brick material. All of these applications share a common parameterized design editing method. Conceptually, the parameters define a high-dimensional design space where every point in that space maps to a visual output. As with other types of design, creating a design in a parameterized space is an iterative process. For example, when creating a futuristic font, solutions that appear to be going in the right direction early in the process may actually be dead ends, as the design goals get continuously updated during the process. Many of these goal updates are often driven by personal preferences. While the design process can seem somewhat random, it is often thought of occurring in three phases, shown here with some 2D representations of a high-dimensional space. Preliminary design, exploring all possibilities in the design space. Refinement, taking a design that has desirable properties and generating alternatives. And detail, making small tweaks to finalize the design. A real-world design process often requires fluidly switching between phases due to changing design goals. In order to best support this design process in parameterized spaces, we build the Domain-Agnostic framework according to three principles. Provide support for guided exploration based on personal intent, allowing users to create variations of current designs and easily explore the design space. Maintain access to low-level controls, as the detail phase is a fundamental part of the process. And ensure that all actions taken in the interface resolve at interactive rates to support fast ideation. Domain-Agnostic is a software framework that enables interactive model-guided exploration of parameterized design spaces. The framework is built around a model of intent, called a design adjective, that can represent a design goal based on a small number of user-labeled examples. Other components interact with the model by sampling from it, arranging the returned samples, providing initial input to the adjective, and allowing for detailed design with access to low-level parameter selection tools at any time. We present a domain-agnostic implementation of the design adjectives framework that uses Gaussian process regression to represent design adjectives. This implementation works with any bounded parameterized design domain. Before describing the framework and our implementation, let's take a look at what kind of interactions this framework enables. In this toy example, I am using our domain-agnostic design adjectives interface to create a yellow brick texture. I first assign high scores to yellow brick textures and low scores to any other color. I then sample from the newly defined yellow brick adjective, which returns a gallery of designs to browse through. I then assign scores to some of the returned designs to refine the design adjective, and repeat the sampling process. Note that the sliders can be used at any time, and update their highlighting when the adjective is updated. Next, let's take a look at the framework components that enable this kind of interaction. The design adjectives framework is built around a design adjective. A design adjective represents a design concept from user-scored input examples. It outputs a numeric score representing how well an arbitrary input matches the current adjective's design goal. Adjectives are trained and updated in real time. Navigating through the design space is done by sampling designs from the design adjective. Users can move through the space relative to the score of the current design by using simple operators, such as similarly scored designs. Designs returned by the sampler are arranged in a design gallery to let users browse through and score designs for adjective refinements. The components described so far have been working with an adjective that already exists. A newly created adjective has no scored examples to sample from, so we need a way to generate initial samples. This is handled by a bootstrapper, which generates such designs. Access to the original parameter space is preserved, as designers often want to fine-tune aspects of their design. For parameter selection tools, such as slider highlighting, can be added to aid this fine-tuning process. Our domain-agnostic implementation provides implementations of each of these components. We use Gaussian process regression to implement a design adjective. Gaussian process regression is a machine learning technique often used to learn preference functions in low data environments. This has been used with success in prior work in computer graphics when learning preference functions from small amounts of user data. Given an input, Gaussian processes return a mean and variance value. In this implementation, we discard the variance and treat the mean value as the preference score. We can now input any design in the space and get a preference value from the adjective. Note that the preference score assigned to an example is not unique. Multiple examples will have similar scores. This is great for us, as we want to be able to show designers a lot of similarly scored things to help refine their design idea. Next, we need to generate design suggestions from our design adjective. We do so with a guided rejection sampler. The idea with this guided sampler is that we know which points in the space are already known to be good. So if we start with that example and randomize some of the other parameters, we'll be more likely to find things that the user will be interested in. Conceptually, this is similar to taking an existing design and modifying it to explore alternatives as part of the refinement process. Here's what that looks like. First, we'll select a random high-scored example. We need at least one of these to run the sampler, so the user needs to provide at least one high-scored example to get started. We'll take some of the parameters in the selected example and randomize them using a uniform distribution. We'll then take the new parameter configuration and use the current adjective to score the results. We then accept or reject the sample according to user-specified criteria. If accepted, the example is added to the set of designs displayed to the user, and if rejected, the process repeats from the top. There are a couple details of the sampling algorithm to make sure returned designs are diverse and get generated in a reasonable amount of time. Please see the paper for additional details. To provide user-directed control over the returned samples, we allow the user to change the acceptance criteria. Different acceptance criteria enable different methods of traveling through the design space. The system provides 4 criteria: towards, away, nearby, and axis. Please see the paper for details about these criteria. When samples get returned from the sampler, we arrange them in a design gallery. We display a simple gallery of samples sorted from best adjective score to worst adjective score. From this interface, users can browse through the results visually and easily provide feedback to the model to update its definition. Everything I've talked about so far related to the adjective assumes that we have defined an adjective to work with. Of course, at the start, the definition is empty, as there are no labeled examples. We need a way to initialize the adjective with some labeled data, and we use the framework's Bootstrapper component to do this. For generic domains, we find that a simple uniform random sampler is sufficient. If we were working with a specific domain, we may be able to provide better preliminary samplers. Finally, we provide a number of tools to help designers manipulate individual parameters during the detailed design phase. One such tool is parameter highlighting. We highlight sliders to indicate the most impactful parameters in a manner similar to Koyama's prior work that does the same with a crowdsourced preference function. We exchange the crowdsourced function with the design adjective model. Our other parameter selection tools are described in our paper. We evaluate the design adjective system through a series of user studies. We ran 2 sets of studies to evaluate the design adjectives framework, 2 case studies with professionals, and a user study where novice to intermediate designers performed simple design tasks. In the professional case studies, a graphic designer and a material designer used the tool for unstructured design tasks in their respective domains. Each designer spent 8 hours with the design adjective interface. Some of the fonts created by the graphic designer are shown here. The professionals provided feedback through interviews. They found that the framework was extremely helpful for design concepting and felt that the system sufficiently captured the intent of their design concepts. Novice designers were given 3 10-minute design tasks. The first 2 tasks used the adjectives interface, and the final repeated the first task with the per-parameter baseline interface. Participants filled out surveys measuring how they felt about the design task they just completed, and interface logs were recorded. The tasks were simple directed design tasks. For example, users were asked to make the font shown here look more futuristic. From this study's survey results and interface logs, we found that users preferred design adjectives for performing exploratory design, that adjectives were perceived to sufficiently represent design concepts, and that the design adjectives interface was more enjoyable to use for these tasks. Please see the paper for complete evaluation details. In summary, We presented the Domain-Agnostic framework for building parameterized design interfaces based on user-guided exploration, and presented a domain-agnostic implementation that uses Gaussian process regression to represent design adjectives. We hope that this framework makes it easier to build and customize principled interfaces for parameterized design. Thank you for watching. You can find additional information and code about the project at the listed URLs, and can contact me, Evan, at the email listed.